The plan for today is to continue talking about normalizing flow models. So recall that in the last lecture, we've sort of like introduced this idea of building a latent variable model that will allow us to evaluate likelihoods exactly, so without having to rely on variational inference. And so it's going to be similar to a variational autoencoder in the sense that there's going to be two sets of variables. There's going to be observed variables x and latent variables z. And the key difference is that the relationship between these two sets of random variables is deterministic. So in a VAE, you would say sample x given z by using some simple distribution like a Gaussian, where the parameters of x given z might depend on the particular value of the latent variables. In a flow model, the relationship is deterministic and invertible. So you obtain x by applying this transformation, which we denote f theta here. And because the mapping is invertible, you can also go back. So inferring the latent variables given the observed one only requires you to somehow be able to compute the inverse of this mapping. And here we're denoting these mappings f theta because they are going to be parameterized using neural networks. And what we'll see today is that we're going to think about ways to parameterize this kind of like invertible transformations using neural networks and then learn them from data essentially. And the nice thing, recall, of using an invertible transformation is that the likelihood is tractable. So you can evaluate the probability that this particular model generates a data point x by essentially using the change of variable formula, which is fairly intuitive. Especially the first piece is very intuitive. You're saying if you want to evaluate the probability of generating an image, let's say x, what you do is you invert to compute the corresponding z, and then you evaluate how likely that z was under the prior, which is this distribution pz. And then recall that this is not enough. If you just do that, you're not going to get a valid probability density function to get something that is normalized. So it integrates to 1 if you go through all possible x's. You have to rescale things by this absolute value of the determinant of the Jacobian of the inverse mapping. And that's basically telling you intuitively what you do is you linearize the function locally by looking at the Jacobian. And then the determinant of the Jacobian tells you how much or how little that transformation expands or shrinks kind of like a unit volume around the data point x. And so it's very similar. Remember, we worked out the example of the linear mapping in the last lecture where we define a random variable by transforming a simple random vector by multiplying it by a matrix. Essentially, this is what's going on here, and you have the same kind of expression. And so the key thing to note is that these can be computed exactly and basically without introducing any approximation to the extent that you can compute these things. You can invert the mapping, you can compute the determinant of the Jacobian. If you can do those things, then you can evaluate likelihoods exactly. So you don't have to rely on variational inference where you had to use this encoder to kind of like try to guess the z given an x, and you had to sort of do that integral because there's many possible z's that could give you any given x. So you don't have to do any of this. And so this is as nice as having something like an autoregressive model where you can evaluate likelihoods exactly just using this equation. And one of the various kind of limitations of this kind of model family is that x and z need to have the same dimensionality. And so that's different from a variational autoencoder where we've seen that z could be very low dimensional and you can kind of use it to discover some compact representation of the data. That's no longer possible in a flow model because for the mapping to be invertible, z and x need to have the same dimensionality. Cool. So now how do we actually do this? I mean, how do we turn this math, this general idea, into a model that you can actually use in practice? Well, the idea is the usual story, kind of like in deep learning, is to combine relatively simple building blocks to define flexible kind of architectures. And so a normalizing flow is essentially a generative model based on where we are going to use essentially neural networks to represent this mapping f theta, which is really the only thing. I mean, you have the prior over z and the f theta mapping. That's the only thing you can really change. And it's called a normalizing flow because the change of variable formula gives us a normalized density if you kind of like account for the determinant of the Jacobian. And it's called a flow, exactly what I was saying, because it's kind of like this deep learning idea of defining the mapping that we need by composing individual blocks, which could be relatively simple. So we're gonna essentially define an architecture where there's gonna be multiple layers of invertible mappings, where we essentially start with a random vector z0, which could be, let's say, described by the prior, a Gaussian or something like that. And then what we do is, or it could even be but depending which way you want to see it, we start on one end with a random vector z0, and then we apply these transformations, f1, f2, f3, fn, all the way through m in this case. And essentially what this notation means is that what we do is we take a z0, we pass it through the first neural network, and then we take the output of that and we pass it to the second neural network, and so forth. And we denote this architecture that we get by stacking together multiple invertible layers, f theta. And it's pretty easy to see that as long as each individual layer is invertible, the combination of multiple layers that you get by doing this kind of operation is also invertible. And so to the extent that we are able to come up with reasonable neural network architectures that define an individual layer, we're going to be able to kind of like stack them together and get something more flexible.
The thetas are not the same in each of the f functions, right? There.
Yeah, so that's a good question. I think this notation is a little bit overloading here the meaning of theta. The parameters of the individual mappings are going to be different, so they are not necessarily tied together. We're going to use theta to denote the union of all the parameters that you need to specify each individual layer. And so that's sort of like the story of this flow of transformations. You start with a simple distribution for z0, the first, let's say at the topmost level of your flow. For example, by sampling from a Gaussian distribution. This is the usual prior, the same thing you had in a variational autoencoder. And then you apply this sequence of invertible transformation to obtain your final sample. And so you feed it through all these different layers, and then let's say after m of them, you get your final sample x. And the good thing is that, if each individual mapping is invertible, then the combination is also going to be invertible. And you can actually work out what's the corresponding kind of like change of variable formula. And to the extent that you understand the determinant of the Jacobian of each individual layer, then you can work out the corresponding determinant of the Jacobian of the combination of these mappings. So all you have to do is you have to be able to invert this function f theta that you get by combining all these neural networks. And if you can invert each individual layer, you can, of course, kind of like invert the full function. And to the extent that you can linearize, basically, and you understand how each of the individual layers behave locally, so you understand how that determinant of the Jacobian looks like, then you can get the determinant of the Jacobian of the full kind of mapping. Right? And this is because, basically the determinant of the product equals the product of determinants. Or equivalently, you can also get this rule, like if you kind of like recursively apply change of variable formula, you get this sort of expression. Or to figure out basically by how much the full mapping kind of like distorts the volume locally. You just need to figure out by how much the individual layers distort the space, and then you just combine kind of like the cumulative effect of all these various layers. And so what this is saying is that we are in a good place if we can somehow define classes of neural networks that are invertible, ideally that we can invert efficiently, and that we can compute the determinant of the Jacobian also efficiently. And here's a kind of like a visualization of this how a normalizing flow works. This is a particular type of normalizing flow called a planar flow. It's not super important, but kind of like to give you the intuition, you start on one end with this random variable z0, which let's say is Gaussian. And then you get a new random variable z1 by transforming it through the first layer, and z2 by transforming the z1 by another simple layer, and so forth. And you can see the effect of these transformations. So you start, let's say, with a two-dimensional random variable z0, which is just a unit Gaussian. So this is just a Gaussian with spherical kind of covariance, which basically has a density that sort of looks like this. There is the mean in the middle, and the probability mass kind of has a relatively simple shape. Right? It's not something you can use to model complicated data sets. But then you apply, let's say, a first invertible transformation, and you get a new random variable z1, which now has a more complicated kind of density. Then you apply another one, and you get something even more complicated. And after 10 layers, after 10 kind of individual, after 10 invertible transformations, you can get something that is much more interesting. Again, it kind of has the flavor of a mixture distribution where you can spread out the probability mass in a much more flexible way.
Is there a proof that we can't go to the 10th transformation using some neural network that can represent all of them at once? Because if I'm thinking about it in terms of simple like functions like matrices, I can sort of show that ABs would have seen like with this curve C instead.
Yeah. So I mean, there is certainly a mapping that could be an invertible mapping that would get you from the beginning to the end, which is just the composition of those neural networks. The beauty sort of like of the deep learning strategy is that the individual layers are going to be relatively simple. So the individual f theta I that we will see are actually relatively simple transformations. Think about, it's not quite linear, but something almost linear. And even though that's simple, by stacking them together, you can get some very flexible kind of transformations. So it's similar to a deep neural network, and maybe the individual layers are not particularly complicated. Maybe it's just a linear combination and a nonlinearity. Then if you stack them together, you can get a very flexible map. And yeah, that's kind of like what's going on here. Yeah.
So you have to place a constraint that the weights are actually invertible themselves, because you could have a sigmoid, which is like a one-to-one mapping. But like, what about like enforcing that full rank assumption? I feel that's where you'd actually have issues.
Yeah. So the question I think is, how do you ensure that if you learn these thetas, you get a mapping that is invertible? And so what we will have to do is we will have to design architectures in a very special way, such that you're guaranteed that regardless of how you choose the parameters, the mapping is invertible. And not only that, we'll also need to be able to invert it efficiently, ideally, because if you need to be able to go both ways. And that's also not enough. You also need to be able to compute that determinant of the Jacobian relatively efficiently, because naively it could take you n cube, where kind of n is the number of variables, the number of dimensions, the number of pixels. That's horrible, basically. So that's what's going to come up next, the kind of like ways of defining these mappings, and then how to learn them from data, which is going to be trivial because we have access to the likelihood. Right. And so here's another example. This is a different, what you see at the bottom, same idea, but the prior is uniform. So here the prior is Gaussian, and we transform it to something like this. Here the prior is a uniform random variable, again, two-dimensional. So all the probability mass is, let's say, between 0, 1, 0, 1. And so it's kind of like a square. And then by applying these invertible transformations, you're able to map it to, again, something much more interesting. And you can see, so it's normalizing because each individual random variable that you get by applying an invertible transformation is automatically normalized by the change of variable formula. And it's a flow because you're applying many transformations one after the other. And so it's kind of like the probability mass is sort of like flowing around through these transformations.
In the examples you showed, are each transformation, are they like the same transformation, or are they different? Do you apply each different transformation?
Yeah, good question. So this is a planar flow, which is one way of defining kind of like an invertible layer through a neural network. And so the functional form is the same at every layer, but the parameters are different, kind of like what was asked before. So it's kind of like the same it's the same layer, but with different parameters. And yeah, so you can see kind of like the takeaway is this is sort of like the intuition. This is the only thing that is easy to visualize, but you can imagine we're going to try to do something similar over a much higher dimensional space where we're going to try to model, let's say, images on the right-hand side. Cool. So how do we do? The first thing is, well, we need to parameterize somehow this mapping, and that's going to be sort of like the main topic of this lecture. The other thing that we need to do is we need to be able to do learning. So once you've defined a space of invertible mappings, how do you choose these parameters theta, ideally to fit some data distribution? And it turns out that that's very easy. Because we have access to the likelihood, we can basically do the same thing that we did for autoregressive models. So the most natural way of training a flow model is to just pick parameters theta that maximize the probability of a given data set, or the log probability of a particular data set. Or equivalently, you go through your data set D and you try to find parameters that maximize the probability assigned to, or the average log probability across all the data points in your data set. So intuitively, you're kind of like trying to find, you have a bunch of data points, which you can think of points in this space, and then you're kind of like trying to find the parameters of the flows to put as much probability mass around the data points that you have in the training set. And the good thing, again, is that unlike a variational autoencoder, we can actually evaluate this likelihood. We can figure out what was the probability of generating any particular data point, X. All you have to do is you use the usual formula of the change of variable formula. So you take the data point, you invert it, you find the probability with respect to the prior, which is whatever, something simple. PZ is, again, kind of like what you have here on the left. Could be a Gaussian, could be uniform, something simple. And then you account for that determinant of the Jacobian, and because it's a log of product, it becomes a sum of logs. And so again, all you have to do is to basically, well, maybe it's on the next, no, okay, it's not on this slide, but basically you have to figure out how much what is the log determinant of the Jacobian for the full transformation, which can also be broken down into the log determinants of the Jacobians of the individual pieces that define your flow model. Then what you do is, if you can evaluate this loss, or I guess this is not a loss because we're trying to maximize this, but if you can evaluate this function as a function of theta, then you can take gradients and you can try to optimize it, essentially. And so to the extent that you can invert this function, and to the extent that you can evaluate those determinant Jacobians term efficiently, we have a loss that we can try to optimize as a function of theta. And so you can do exact loss likelihood evaluation by using this inverse mapping. So go from data to prior. And then after you've trained the model, you can generate new samples. So you want to generate new images, or you want to generate new speech or sound or whatever you're trying to model. Then we know how to do it. It's just basically just the forward direction, just like in a VAE. That has not changed. you sample Z from the prior, and then you transform it through your mapping. And that produces an output. And if you care about getting latent representations, kind of like in a VAE you would use the encoder to try to infer Z given X. In a flow model, it's relatively, again, easy to figure out what is the corresponding Z for any particular X. All you have to do is you have to invert the mapping. But again, it's questionable whether this can be thought as a latent variable because it has the same dimension as the data, and so it's not going to be compressed sort of like in any way. Yeah.
But like there surely is like some structure, right? Because after all, we even if it's one-to-one, it's no longer random. So there might be something.
Yeah. So I'll show you that training models on images, and then you can do interpolation in the latent space, and you get reasonable results. So it's certainly doing something meaningful, but it might not be compressive as you would expect a VAE, for example. So it's a different kind of latent variable, but it's still a latent variable for sure. Okay. Yeah.
So we parameterize both the f theta and the inverse process, right?
So good question. I mean, do we parameterize f theta or do we parameterize f theta inverse? You only parameterize one because the other one is obtained kind of like directly by hopefully it's really invertible, and so hopefully you can actually do it. But it's a good question whether you should parameterize f theta like the direction that you need for sampling, or should you directly parameterize the inverse because that's kind of like what you need during training. And so those are two valid choices, and there might be. I mean, if you have to, let's say, numerically invert a function, maybe it's invertible, but maybe it's not cheap. And that maybe computing an inverse requires you to solve a linear system of equations or something, right? It's invertible, it's possible to compute this f theta minus inverse, but it's maybe too expensive if you have to do this over and over during training. Maybe depending on what you want to do, you might want to parameterize one or the other, or you might choose an f theta that can be inverted very quickly. And so we'll see the kind of trade-offs that you get by doing one or the other.
Should f theta inverse have the same form as V? As like in VAs we had a considered divergence loss between them to ensure that they were roughly the same. Is that something you can do?
So the question is, well, what if it's not quite fully invertible, or could you parameterize both and try to make them one the inverse of the other? People have explored these kind of things where then they try to make sure that kind of like you can do both directions, and we'll see other way of kind of like distilling models that can be efficiently evaluated in one direction into ones that can be efficiently evaluated in the other direction. So yeah, we'll talk a little bit about this. Cool. All right. So what do we want from a flow model? We have a simple prior that you can sample from efficiently, and you can evaluate probabilities because we need that PZ here. When you do this formula, you need to be able to evaluate probabilities under the prior. So typically something like a Gaussian is used. We need invertible mappings that can be tractably evaluated. So if you want to evaluate likelihoods, you need to be able to go from, let's say, X to Z efficiently, or as efficiently as possible. But if you want to sample, then you need to do the opposite. So again, kind of going back to what we were just talking about, two things, depending on what you want to do or depending which one you want it to be as fast as possible, you might want to do one or the other. And then the other big thing is that we need to be able to compute this determinant of Jacobians. And these Jacobian matrices are pretty big. They're kind of like n by n, where n is the data dimensionality. And if you recall, if computing the determinant of a generic n by n matrix takes order of n cube operations. So even if n is relatively small, like 1,000, this is super expensive. So computing these kind of determinants naively is very, very tricky. And so what we'll have to do is we'll have to choose transformations such that not only they are invertible, but the Jacobian has special structure, so then we can compute the determinant more efficiently. And the simplest way of doing it is to choose matrices that are basically triangular, because in that case, then you can compute the determinant in basically linear time. You just multiply together the entries on the diagonal of the matrix. And so one way to do it is to basically define the function f such that basically the we want to make sure we want to define a function f basically, which again has n inputs and n outputs, such that the corresponding Jacobian, which is this matrix of partial derivatives, is triangular. So there needs to be a lot of zeros basically in the matrix. And one way to do it, and recall the Jacobian looks like this. So for f, this is a function, f is a vector valued function, has n different outputs. So there is kind of like n functions, scalar functions, f1 through fn, and the Jacobian requires you to compute basically the gradients with respect to the inputs of each individual function. So you can think of each of these columns as being the gradient of a scalar valued function with respect to the inputs, now with respect to the parameters. And a triangular matrix is basically a matrix where all the elements above the diagonal, let's say, are 0. And so any guess on how do we make, let's say, the derivative of f1 with respect to zn 0? Yeah, it just doesn't depend on it, right? And so if you choose kind of like the computation graph such that the ith output only depends on the previous kind of inputs, kind of like in an autoregressive model, then by definition, all the derivatives, a lot of the derivatives are going to be 0, and you get a matrix that has the right kind of structure. So it's lower triangular. And if it's lower triangular, you can get the determinant just by multiplying together all the entries on the diagonal. And there is n of them, and so it becomes linear time. And so that's one way of getting efficient kind of efficiency on this type of operation, is to choose the computation graph such that it kind of reminds us a little bit of autoregressive models, in the sense that there is an ordering, and then the ith output only depends on all the inputs that come before it in this ordering. And yeah, and of course you can also make it upper triangular. So if xi, the ith output, only depends on the entries the inputs that come after it, then you're going to get a matrix that is going to be upper triangular, and that's also something that you can evaluate the determinant in linear time. So just to recap, normalizing flows transform simple distribution to complex with a sequence of invertible transformations. You can think of it as a latent variable model with exact likelihood evaluation. We need invertible mappings and somehow Jacobians that have special structure so that we can compute the determinant of the Jacobian in the change of variable formula efficiently. And what we're going to see today is various ways of achieving it. There's a lot of different kind of neural network architectures or layers that you can basically use that sort of like achieve these sort of properties. And the simplest one is something called nice. And then here you can see more. Let's see nice. The simplest way of doing this is something like this. It's an additive coupling layer. So what you do is you partition these z variables into two groups. Again, there is an ordering of the z variables, and you take the first d, z1 through zd, and then the remaining n minus d. So you have two groups of the z variables, and you pick a d. It can be anything. And then to define the forward mapping that gets you from z to x, what you do is you keep the first d components unchanged. So you just pass them through. And then you modify the remaining components, the remaining m minus d components, in the simplest possible way, which is just to just shift them. So there is a neural network, which can be basically arbitrary, which I'm calling m theta, which takes the first d inputs to this layer and computes n minus d shifts that then you apply to the remaining n minus d z variables. So you can see that the first d components remain the same, that you just pass them through. The remaining n minus d components, you obtain them just by shifting the inputs by a little bit. And by how much you shift the inputs can be a learnable parameter. Now, is this mapping invertible? It's pretty easy to see that it's invertible. And how do you get the z if you had access to the x? So how do you get z1 through d if you have access to the x? Well, the first d components are not changed, so you just keep them. It's just, again, the identity transformation. How do we get the remaining? If you want to compute z, d, the n minus d inputs, given all the outputs, how do you get them? You just basically subtract, you just reverse this thing. You just write a z equals x minus m theta. And crucially, we can compute m theta because we know the x, because the first d components in the input and the output are the same. So when we do the inversion, we know by how much we should shift, because we're just passing through the first d components. And so we can apply this shift by doing this. You can just subtract off m theta, and we can compute m theta as a function of x1 through d, because x1 through d is the same as z1 through d, which is what we used to compute the shift. And m theta here can be an arbitrary function, can be an arbitrary neural network, basically. Now, what do we need to, the other thing we need to figure out is, can we compute the Jacobian of the forward mapping? So what are the matrices of partial derivatives? It has sort of like the right triangular structure. And you can see that the only thing that we're doing is shifting. And so when you look at the partial derivatives of what happens on the diagonal, it's just all going to be identity matrices. Right? So if you look at how does kind of like the function on the second line here depend on the various z's, on the later z's, you see that it's just a shift. So that matrix of partial derivatives that you get here at the bottom right is just another identity matrix. And so what this means is that, what is the determinant of the Jacobian of this matrix?
1.
It's just 1, like it's the product of all the elements on the diagonal. They are all 1s, and so the determinant of Jacobian is 1, which means that it's trivial to sort of like compute this term in the change of variable formula.
Here it seems like z and x are, so connected that how can we find like an easy distribution from where we can sample, like, will z ever take a Gaussian form since like z and x are so?
Yeah, so great question. I mean, is this flexible enough? I'll show you some empirical results that, this model is not the best one. It's probably the simplest you can think of, but it's already quite powerful. You can actually already use this to model images, which is pretty surprising, because it means that by stacking a sufficiently large number of these very simple layers, you can actually transform a complicated distribution, like over images, into, let's say, a Gaussian. Yeah?
Well, if we have the ith output not dependent on the ith, we put some entries have a 0 diagonal, so it's just always 0.
Say again?
What if we have a diagonal entry that's just 0, and then the determinant is always 0? So what's that?
It basically means that it's not invertible. If you have zeros on the diagonal, it basically means that. And now this is called a volume preserving transformation, because recall that basically if the determinant is 1, it means that you're not expanding that unit hypercube, or you're not shrinking it. It just kind of like stays the same. but you can move around kind of like probability mass. And now the final component, that you use in this model called NICE is rescaling. So you can basically imagine many of these coupling layers where you can change the ordering of the variables in between. So you don't have to keep the same ordering in every layer. You can pick them any order you want is fine, as long as you satisfy that kind of property that we had before. And then the final layer is rescaling. So again, something super simple. You just element-wise scale all the entries with some parameters, SIs, which are going to be learned, and it's just a scaling that you apply. So again, the simplest kind of like transformation you can think of. What is the inverse? Again, you just divide by 1/s. So trivial to compute the inverse mapping. And the determinant of the Jacobian, well, if you think about the matrix of partial derivatives, is a diagonal matrix. On the elements on the diagonal are these SI terms. And so what is the determinant of of a diagonal matrix? It's just going to be, again, the product of all these SIs, basically. So and you might think this is super simple. How can you possibly learn something useful with a model like this? But if you stack enough of these layers, you can actually learn some decent models. And so if you train a nice model on MNIST and then you generate samples, they look like this. You train it on faces, you can get samples that sort of like look like that. So not the best generative model, of course, but it's already somewhat promising that something so simple can already figure out how to map a complex distribution over pixels into a Gaussian, basically, just by stacking a sufficiently large number of simple coupling layers like the one we saw before. Yeah.
What would be the Z that we would use for generation in this case?
Depends what you choose for the prior. In this model, you would typically use a Gaussian, univariate, like a unit Gaussian. So that's what you would use.
Like an image of the same dimensions.
Same dimension, every entry is Gaussian, and if you have unit covariance, then you can just sample each component independently. And then, so you start with pure noise, then you feed it through the inverse mapping, which we know how to compute because we know how to, if you want to, you just invert layer by layer. The final layer, you invert it like this. The previous layers, you invert them by applying this transformation. And then you gradually turn that noise into an image, essentially. Yeah.
Since the first half of its identical transformation means when we generate the image, we basically provide the first half as given information.
Yeah, and the question, is because the first D components are not changed, then we're basically passing them through, and it doesn't have to be half. It can be any D. You can be an arbitrary fraction that you're basically keeping unchanged, and then you modify the rest by just shifting, essentially. Okay, so that's perhaps the simpler, and here you can see other examples. If you train it on a data set of SVHN, these are like house numbers. If you train it on CIFAR10, again, not the best kind of samples, but it's kind of doing something. You can kind of see numbers here in different colors on the left. Kind of see samples on the right. Now, what's the kind of like natural extension of this? Instead of just shifting, we can shift and scale. And that's a much more powerful model called Real-NVP, which is basically essentially identical to NICE, except that at every layer, we don't just shift, but we shift and scale. So the forward mapping is kind of like before. We pass through the components. So we apply an identity transformation. And then for the remaining ones, instead of just shifting, we shift, which is now this neural network mu theta, which is the same m that I had before. But now we also element-wise scale each entry. And again, the scaling coefficients are allowed to depend in a complicated way on the first d components. As long as, and I'm taking an exponential here so that I'm guaranteed that these scaling factors are non-zero, and then I can invert them. But essentially, these matrices, mu theta, alpha theta, can be anything. How do we invert the mapping? Again, it's the same thing, right? So yeah, these are neural networks, arbitrary parameter, basically arbitrary neural networks, and they're parameterized by theta, and that's what you actually learn. How do we get the inverse mapping? How do we get z from x? Again, the first d components, you don't do anything. You just look them up, and it's, again, an identity mapping. And then for the second one, you have to figure out how do you recover z given x. And so what you do, you take x, you shift it by mu, and then you divide by exp of alpha, and that gives you the z, like element-wise, right? So, which equivalently is sort of like this. You take the x, you shift it by mu, and then you multiply by e to the minus alpha, which is the same as dividing by e to the alpha, which is dividing by the coefficients that you're multiplying for here. So again, trivial, very easy to do the forward, very easy to do the inverse. What about the determinant of the Jacobian? What does the Jacobian look like? Again, it has the nice property that it is lower triangular. And now it's a little bit more complicated, the way you operate on these z's, because now there is a shift, there is a scale, which is kind of like the last layer of nice, except that it's learned. And so it's kind of like what we were doing before. Before we were just shifting. Now we're shifting and scaling, and so you have all these extra kind of scaling factors that you're applying to the last n minus d dimensions of the data. And again, this is just what you would get if you compute partial derivatives of these outputs with respect to the inputs, you're going to get this kind of expression. And how do you get the determinant? Well, you multiply together a bunch of ones, and then you multiply together all the elements of the diagonal of this diagonal matrix. And so it's just going to be the product of the individual scaling factors that you apply on every dimension, or equivalently, it's kind of like the exponential of the sum of this log kind of parameterization. So basically, you can choose arbitrary neural networks, mu theta, alpha theta, and if you apply that kind of transformation, you get something that is invertible. It's easy to compute the forward mapping, it's easy to compute the reverse mapping, and it's easy to figure out by how much it shrinks or expands, kind of like the volume locally, which is just these scalings. So if the scalings are all 1, then it's the same as a coupling layer that we had before. But because alpha thetas are learned, this is strictly more flexible than what we had before, because it can learn to shrink or expand kind of certain dimensions. And of course, this is in general non-volume preserving, because in general, this determinant of the Jacobian is not always 1. So it can do more interesting kind of transformations. Yeah.
Would we be assuming that we pre-sample the latents in images? So basically saying that for every Z, like let's say we sample MCs and associate an image for each of them? Because to me it seems if you have an invertible transformation, and you need to actually also sample your Z's and associate each of them to an image, would that be an issue over here or not really?
So to sample, what you would do is you would randomly draw a Z, and then you would pass it through this inverse map, I guess. No, I'm parameterizing the forward, so you would just pass it through the forward map.
I guess, sorry, I meant during training. During training, you pre-sample your Z's or just do it dynamically?
So during training, you don't have to, the Z's are computed by inverting the mapping. So the Z's are obtained from the data. So you just feed kind of your image at the one end of this big invertible neural network, and then you hopefully are able to invert it. And if each individual layer has this kind of shape, then you know how to invert it, and then you get a z at the end. You evaluate how likely the z is under the prior, and then you account for the local shift and change that you get through the change of variable. So it's not like in a VAE where you have to guess the z. You get it exactly through the invertible mapping. Yeah.
Can I say during inference, when we sample a z, and then the generation process is actually deterministic?
Yes. So the generation process is deterministic given a z because the mapping itself is deterministic. That's a big limitation, but it's also what gives you tractability, basically. Okay. Now, this is a model that works much better. Here you can see some examples. Again, this might seem like a very simple kind of transformation that you're applying to the data, but if you train these models on image data sets, this is starting to generate samples that are much better in terms of quality. Like you can see on kind of bedrooms or people. These models are pretty decent. They're still somewhat low resolution and everything, but it's generating samples that have kind of like the right structure. They're already pretty decent.
Which part is input and which part is?
I think you get the samples. These are the training samples, and these are the generations that you see on the right. So maybe the first line, the first row not so good, but for the bedrooms, I think this is Elson, this is Celebi. I think you can see that is pretty decent. Yeah.
How many layers are these models being used?
Good question. I don't remember how many layers they use, but a pretty decent number. Yeah. Yeah.
You mentioned like the different layers will have different parameters, so they're not kind of sharing.
They're not sharing.
Oh.
Yeah. And back to the question of what do the z's actually mean? What you can try to do is you can try to interpolate between different z's, and what they show in this paper is that basically if you start with the 4 actual samples, which are shown at the corner of this image here, and then you get the corresponding z vectors, which are z1, z2, z3, z4, but just by inverting the network, and then you interpolate them using this kind of strange formula, which is because the latent space is Gaussian. It doesn't matter too much. And then you get new z's, and then you pass them through the forward mapping to generate images. You kind of get reasonable interpolations. You see that you go from one image from one person kind of to another person, and it slowly kind of like drifts from one to the other. And you can see examples here on these kind of like buildings, and you can see, so basically in each of these images, the 4 corners are real images, and what you see in between is what you get if you were to interpolate the z vectors of 2 real images and then decode them back into an image. So even though, yeah, the latent variables are not compressive, they have the same number of variables, they have kind of like meaningful structure, kind of like as we were discussing before, in the sense that if you do interpolations, you get reasonable results. Okay, now what we can see is, that actually autoregressive models, or certain kinds of autoregressive models, you can also think of them as normalizing flows. And so just to say this, you can think about an autoregressive model, a continuous one, where we're defining the density, the full joint, as a product of conditionals. And let's say that each conditional is a Gaussian with parameters computed as usual by some neural network that takes as input the previous variables and then computes a mean and a standard deviation. And that's how you define the ith conditional in your autoregressive model. So this is not kind of like the language model version where each of these conditionals is like a categorical distribution. This is the continuous version where the conditionals themselves are, let's say, Gaussians in this case. And what I'm going to show you next is that you can think of this actually as an autoregressive model, as a flow model. Like you can this as defined like this is just an autoregressive model. You can think about how you would generate samples from this model. And the way you would generate samples is something like this. You could imagine generating in one sample from a standard normal distribution for every I, for every component, for every random variable, individual random variable that you're modeling. And then what you do is, well, to sample from the conditionals, you have to, the conditionals are Gaussian with certain means and standard deviations. So kind of like using the reparameterization trick, you can obtain a sample for the, as usual, you sample the first random variable, then you sample the second given the first. And to do that, you need to sample from these Gaussians, which have certain means and certain standard deviations. So you would generate a sample from, let's say, the first pixel or the first random variable by just shifting and scaling this unit standard random Gaussian random variable, which is just Gaussian distributed. So it's starting to look a little bit like a Real-NVP kind of model, right? Where you have the Z's and then you shift and scale them. How do you sample x2? Well, you sample x2 given x1. So you take the value of x1, you feed it into these two neural networks, you compute the mean and the standard deviation of the next conditional, and then you sample. And so you do that, and then you sample x2 by shifting and scaling this unit random variable z2. Right? Remember that if zi is a Gaussian with mean 0 and standard deviation 1, if you shift it by mu2 and you rescale it by this constant, you get a Gaussian with the right mean and the right standard deviation. And again, it feels a lot like a normalizing flow model that we saw before. Given x1 and x2, we can compute the parameters of the next conditional, so a mean and a standard deviation, and we can sample the third, let's say, pixel by shifting and scaling these basic random variable z's that we had access to. And so, all in all, we can kind of think of sampling what you get by sampling from this autoregressive model as a flow, in the sense that you start with this random vector of simple normals, and then you shift them and scale them in some interesting way using these conditionals, using these neural networks mu and alpha that define the conditionals in the autoregressive model. Like these two, like sampling the autoregressive model just by going through the conditionals one at a time is equivalent to doing this, which you can think of as taking a bunch of simple random variables, zi's, all just Gaussian, independent of each other, and then you just feed them through this interesting kind of transformation to get your final output x1 through xn. Questions on this? I see some confused faces. Yes.
Like, how can we get all of them like backwards? Like, won't we need like one?
Let's see. How do we invert it? Yeah, great question. I think that's when I come next. The forward mapping, again, you can kind of think of it as a flow that basically does this. You use the z's to compute the first x, and then what you do is you compute the new parameters, and then you get the new x, blah blah, and you can kind of see that sampling in this model is slow, like in all autoregressive models, because in order to compute the parameters that you need to transform sort of like the ith simple prior random variable zi, you need to have all the previous x's to figure out what's the right shift and scale that you need to apply. What is the inverse mapping? How do you go from x to z? Well, the good news is that you can compute all these mu's and alphas in parallel, because once you have the image, you have all the x's, so you can compute all the mu's and alphas, or the shifts and scales, in parallel. And then you compute the corresponding z's by just inverting that shift and scale transformation. So if you recall, if you want to compute z1 from x1, what you do is you take x1, you subtract mu1, and you divide by this exponential, by the scaling. Just like in Real-NVP, that's how you do the transformation. And so sampling, you can see you go from z to x, and you kind of like need to do one at a time. But because these alphas and mu's depend on the x's at kind of inference time or during learning, you can compute all the mu's and alpha in parallel. And then you can compute the z's, again, all in parallel, just by shifting and scaling. And then, the Jacobian is still lower diagonal, and so you have an efficient determinant computation, and so you can evaluate likelihoods efficiently in parallel, just like in an autoregressive model. Right? If you remember, the nice thing about an autoregressive model is that in principle you can evaluate all the conditionals in parallel because you have all you need. Like you know how to compute. Once you have all the whole x vector, you can compute all the conditionals, and you can evaluate the loss on each individual component of your random variable, and the same is true here. So you can basically define a model to kind of like inspired by autoregressive models, which is called a masked autoregressive flow, MAF, that basically transforms simple random variables, z into x, or equivalently x to z's. And if you parameterize it this way, then you can get efficient learning, basically, because you can go from x to z very efficiently in parallel. But as expected, kind of sampling is low because it's just an autoregressive model at the end of the day. And so if you want to sample, you kind of have to go through this process of basically transforming each individual zi variable one at a time. So this is basically just interpreting an autoregressive model as a flow model, and it inherits the properties of autoregressive model, which is the same model. So sampling is sequential and slow, but as expected, you can evaluate likelihoods because it's just basically change of variable formula. So it's possible to actually compute all these the likelihoods exactly like in an autoregressive model. And so this is another way of building a flow model, which is basically you start with an autoregressive model, a continuous one, and then you can essentially think of it, at least if it's a Gaussian autoregressive model, you can kind of like interpret it as a continuous, as a normalizing flow model. The other thing you can do is, if you need a model that you can sample from efficiently, we know that one of the issues with autoregressive models is that sampling is kind of slow because you have to generate one variable at a time. If you just, once you start thinking of an autoregressive model as a flow model, you can just kind of turn this picture around and call the x a z and the z an x. And at that point, it's just another, invertible transformation. So which one is the input, which one is the output doesn't actually matter. It's just an invertible neural network, and you can use it one way or you can use it the other way, and it's still an invertible neural network. And if you do that, you get something called an inverse autoregressive flow, which is basically just the same neural network used in the other direction, where if you do it in the other direction, now you're allowed to do the forward mapping from z to x in parallel. So you can actually generate in a single shot, essentially. You can generate each component of the output in parallel without waiting for the previous entries. Because we know that the computation in that direction is parallel. You basically, you can sample all the z's independently from the prior, and if the mu's and alphas depend on the z's, then you already have them, and you can compute all of them, again, in parallel, and then you just shift and scale all the outputs by the right amount, and then you produce a sample. And so if you basically flip things around, you get a model where you can do very efficient sampling. It's no longer sequential like an autoregressive model, but everything can be done in parallel. Of course, the downside of this is that now inverting the model is sequential. So it's still an invertible mapping, but now if we want to go from X to Z, let's say because we want to train this model, so we want to do maximum likelihood training, then we need to be able to go from images, let's say from X, to latent variables. And that, you have to be able to do it for every single data point. And if you try to figure out what does the computation graph look like, you can see that it becomes sequential. Because what you have to do is you have to shift, you have to compute Z1 by inverting this relationship. So you take the first pixel, you shift it and scale it, and you get the new latent variable. Now you can use that latent variable to compute the new shift and scale for the second dimension. These mu's, they still depend, the alphas and the mu's depend on the previous variables. So now that you have Z1, you can compute mu2 and alpha2. And now you can shift and scale x2 to get Z2. And now you can use Z1 and Z2 to compute the new shift and scale, and so forth. So that's basically the same thing you would have to do that you normally do when you sample out from an autoregressive model. So you have to kind of generate one variable at a time. Here you have to invert one variable at a time before you can invert the next one. And so this is a great model that allows you to sample very efficiently, but it's very expensive to actually compute likelihoods of data points. So this would be a tricky model to use during training, because you would have to kind of like go through each individual variable to be able to invert and to be able to compute likelihoods. The good thing is that it's actually fast to evaluate likelihoods of a generated point. So if you generate the data yourself, then it's easy to evaluate likelihoods because you kind of already have all the z's. Then you map them to X, which you can do efficiently. If you store the latent vector that you use to generate a particular data point, then you don't have to recompute it. You already have it. And so you can actually evaluate likelihoods of data points you generate yourself very efficiently. Because all you need is, you need to be able to evaluate the likelihood of this Z1 through Zn under the prior. You need to be able to evaluate the determinant of the Jacobian, which depends on these alphas, and which you can compute because you have all the Z's to begin with, if you generate a data point yourself. And we'll see that this is going to be somewhat useful when we talk about how to distill models, so that if you have a model that is maybe autoregressive and is slow to sample from, we're going to see that it's possible to distill it into a model of this type, so a different kind of flow that after you've trained a model, kind of like a student model that is much faster than the teacher model that you train sort of autoregressively, and can generate sort of like in one shot in parallel, kind of like this. And yeah, this property at the end here, the fact that you can evaluate likelihoods of points you generate yourself, is going to be useful when we talk about that. And again, sort of like these two normalizing flows, MAF, IIF, are actually the same model essentially, right? It's just if you swap the role of X and Z, they are essentially the same kind of thing. If you think of it from the perspective of MAF, then you compute the alphas and the mu's as a function of the x's, and that's sort of like the way you would do it in an autoregressive model. If you just flip things around, you can get an autoregressive an inverse autoregressive flow by just having the mu's and the alphas depend on the z's, which is basically what you get if you relabel z and x in that figure. And so that's another way to get a flow model, is to basically start with a Gaussian autoregressive model, and then you can get a flow model that way. And yeah, and so they're essentially dual. They're essentially the same thing. And so the trade-offs, sort of like our MAF, it's basically an autoregressive model. So you have fast likelihood evaluation, slow sampling, one variable at a time. IIF is the opposite because it's the reverse. So you can get fast sampling, but then you have a slow likelihood evaluation. MAF is good for training because you can, what we need to be able to evaluate likelihoods efficiently for every data point if you want to do maximum likelihood training. And so MAF is much better for that. On the other hand, if you need something where you need to be able to generate very, very quickly, IIF would be a better kind of solution. And natural question, can we get the best of both worlds? And that's sort of like what they did with this parallel WaveNet, which used to be like a state-of-the-art model for speech generation. And the basic idea was to start with a really good autoregressive model, and then distill it, which is just a MAF, basically, and then distill it into an IIF student model that is going to be hopefully close to the teacher, and it's going to be much faster to generate samples from. And so that's basically the strategy they used. They used an MAF, which is just an autoregressive model, to train a teacher model. This, you can compute likelihoods efficiently. It's just an autoregressive model, so it's easy to train the usual way. And once you've trained this teacher, you can train a student model to be close to the teacher, but because it's an IIF model by design, it would allow you to sample much more efficiently. And the key observation that we mentioned before is that you can actually evaluate likelihoods on your own samples. So if you generate the samples yourself, you can actually evaluate likelihoods efficiently. And then basically one way to do it is to this objective function, which is basically based on KL divergence, where what you would do is you would first train the teacher model by maximum likelihood. This is your autoregressive model that is expensive to sample from. And then you define some kind of KL divergence between the student distribution, which is an IIF model efficient to sample from, and the teacher model. And this is just the KL divergence between student and teacher. And this is important that we're doing it in this direction. You could also do KL divergence teacher-student, but here we're doing KL divergence student-teacher. And the KL divergence, if you expand it, it basically has this form. And you can see that this objective is good for training, because what we need to do in order to evaluate that objective and optimize it is we need to be able to generate samples from the student model efficiently. The student model is an IIF model, so it's very easy to sample from. We need to be able to evaluate the log probability of a sample according to the teacher model. That's, again, easy to do because it's just an autoregressive model, so evaluating likelihoods is easy. To evaluate the likelihood of the data point that you generate yourself using the student model, which is what you need for this term, again, that's efficient to do if you have an IIF model because you've generated the samples yourself, so you know the Z, so you know how to evaluate likelihoods. And so this kind of objective is very, very suitable for this kind of setting where the student model is something you can sample from efficiently from, you can evaluate likelihoods on your own samples efficiently, and then you have a teacher model for which you can evaluate likelihoods. Maybe it's expensive to sample from, but we don't care because we never sample from the teacher model. You just need to be able to do good MLE training, which we know we can do with autoregressive models. And to the extent that this KL divergence is small, then the student distribution is going to be close to the teacher distribution. So if you sample from the student model, you're going to get something similar to what you would have gotten if you were to sample from the teacher model, but it's much, much faster. And all the operations that you see there, they can be implemented efficiently. And that's kind of like what they did for this parallel WaveNet. You train a teacher model by maximum likelihood, and then you train a student IIF model to minimize the scale divergence. And at test time, then you throw away your teacher, and at test time, what you put on the on mobile phones to generate samples very efficiently is to use the student model.
I am wondering in the computation, so like we use the IAF first to sample, then to assign density. When doing back propagation, do we also like update the parameters for the density calculation part of the student, not only the sampling part?
Yes, so you do optimize this function. So you do need to optimize both the sampling and, but you don't need to optimize T. T is fixed. And because everything can be reparameterized, so you can still back propagate through that. Because essentially it's just kind of like a big reparameterization trick that you're doing on the student model. It's starting with simple noise and then transforming it. And so it's easy to figure out how, if you were to update the parameter of the student model, how would the sample change? You can do it in this case because it's the same as reparameterization. And yeah, that's what they did, and they were able to get very, very impressive speedups. This was a paper from Google a few years ago, and that's how they were able to actually deploy the models in production. They trained a really good teacher model by training it autoregressively. That was too slow to generate samples, but then by thinking it as a kind of like from this flow model perspective, then there was a pretty natural way of distilling down into something similar, but that has kind of like the opposite property of being able to sample efficiently, even though you cannot get likelihoods. If you just care about inference, you just care about generation, that's a more convenient way of kind of like parameterizing the family of distributions.
Is it possible to do something similar for language models?
That would be great. The problem with the question is, can we do this for language models? The problem is that if you have a language model that's discrete, and so you can't necessarily think of it as a flow model, and so there is not, you can't really think of sampling from a language model as transforming a simple distribution, at least not in a differentiable invertible way, because the X is discrete, and so there is not really a way to transform a continuous distribution into a discrete one. And so you can't do it this way, basically, unfortunately.
Like, why not being continuous with doing this flow model interpretation?
Yeah, I mean, for flow models, the flow models are only applicable to probability density functions. So you cannot apply them to probability mass functions where you would have discrete random variables. So it's only applicable to continuous random variables. Because otherwise the change of variable formula does not apply. So you cannot use it anymore.
So you cannot get the IAF essentially.
Essentially, yes. Cool. So that's another family. And now for the remaining few minutes, we can just go through a few other options that you have if you want to build invertible mappings. One natural thing you might want to do if you start thinking of, okay, autoregressive models are basically flow models. We know that you can build, you can use convolutional networks in autoregressive models as long as you mask them in the right way. And so the natural thing you can ask is if it's possible to define invertible layers that are convolutional in some way, because we know convolutions are great. And by itself, a convolution would not be invertible. But if you mask it in the right way, you can kind of like get the structure, the computation structure of an autoregressive model, and you can build up a layer that is actually invertible. And if you do things in the right way, you can actually make it such that it's not only invertible, but you can actually evaluate the determinant of the Jacobian efficiently. And kind of like in autoregressive models, like in pixel CNN, really all you have to do is you have to mask the convolutions so that there is some kind of ordering. So then that would give you it would not only allow you to invert things more efficiently, but it would also allow you to compute the determinant of the Jacobian efficiently, because it basically makes the Jacobian lower triangular, and so then we can compute Jacobians determinants efficiently. And yeah, which is what I just said. And basically what you can do is you can try to enforce certain conditions on the parameters of the neural network so that the transformation is guaranteed to be invertible, and you can read the paper for more details, but essentially what it boils down is something like this, where if you have a 3-channel input image, like the one you have on the left, and you have, let's say, a 3x3 kernel, convolutional kernel, which looks at, let's say, R, G, and B, what you can do is you can mask the parameters of that kernel, which in this case is just like this cube. There is a cube for the 3 channels, and you can mask them so that you only look at the pixels that come before you, basically, in the ordering. So you can see sort of like the receptive fields of these kernels here on the right. And when you produce the 3 values on the 3 channels, they are produced by a computation that is basically consistent with this ordering. And you can see that just like in the pixel CNN, you have to decide on which colors you start from, and then you have to be kind of causal also with respect to the channels that you have in the image. Yeah, so basically there are ways to define convolutional kernels that would give you invertible mappings, and you're losing out something because you have the receptive fields now. You're no longer be able to kind of like look at everything in the image. You're kind of restricted in what you can look at, but what you gain is that you get a tractable Jacobian, basically. And you can build a flow model by stacking these kind of layers, and this works reasonably well. Here are some examples on MNIST samples, CIFAR10, ImageNet, samples that you get by training basically a flow model where you have all these convolutional layers that are crafted in a certain way so that the filters are basically invertible. The other quick thing I wanted to mention is kind of like a different perspective on what happens when you train a flow model. This idea that you can either think about training a model such that the distribution of the samples that you get is close to the data distribution, or you can think of training the model as basically saying, if I were to transform my data according to the inverse mapping, I should be getting something that is close to the prior of the flow model, as close to, for example, a Gaussian distribution. So you can use this dual perspective to construct other kinds of layers that can get you, that basically try, where every layer is kind of like trying to make the data look more Gaussian, essentially. And the basic intuition is something like this. If you have a flow model where you transform a Gaussian random variable into data X, and then you have some true data distribution, so a true random variable X tilde, which is the one that is distributed really according to the data. If you do maximum likelihood training, what you do is you minimize the KL divergence between the data distribution and the distribution that you get by sampling from this model, right? By transforming Gaussian noise through this invertible mapping F theta. Or equivalently, you're minimizing the KL divergence between the distribution of the true X tilde, which is distributed according to the data, and this new random variable X that you get by transforming Gaussian random noise. And which is basically, this is saying that if you take Gaussian samples and you transform them through this mapping, you should get something close to the data. Equivalently, you can also, because of properties of the KL divergence, which is invariant to invertible transformations, you can also think of this as trying to minimize the KL divergence of what you get by transforming the true data according to the inverse mapping and transforming the samples through the inverse mapping. And we know what we get if we transform samples through the inverse mapping, we get the prior. And so equivalently, you can kind of think of training a flow model as transforming this data through this random vector x tilde, which is distributed according to the data, into one that is distributed as a Gaussian. So you can think of the flow model as basically Gaussianizing the data. You start out with a complicated distribution, and if you go through the flow in the backward direction, you're mapping it into something that has to look like a Gaussian. And how to achieve this? One natural way of doing it is to basically, at least if you have one-dimensional data, is through the inverse CDF. And so, going through quickly because I don't have time, but if you have a random variable that has some kind of data distribution, if you apply the inverse, or I guess the CDF of the data, there's going to be a CDF for the data distribution. And if you apply the CDF of the data distribution to this random vector or random variable, you're going to get a uniform random variable. That's basically the way you sample from a it's one of the ways to sample from a random variable with known CDF. You sample uniformly, you inverse the CDF, and you get a sample from x tilde. And so basically this kind of transformation where you are transforming a data sample through the CDF, which is kind of like a way to kind of whiten the data, right? It's kind of like the thing you would do by subtracting the mean divided by the standard deviation. Something similar, if you apply this kind of transformation, you get something that is uniform. So it's guaranteed to be between 0 and 1. And once you have a uniform random variable, what you can do is you can apply the inverse CDF of a Gaussian, and you can transform it into something that is exactly Gaussian. And this, so basically the composition of the true CDF of the data and the inverse CDF of a Gaussian will transform any random vector into a Gaussian one. And that's basically the idea of Gaussianizing flows, is that you stack a bunch of transformations, trying to make the data more and more Gaussian. And these are, I guess I'm gonna skip this, but if you know about copula models, these are like a famous kind of statistical model that's often used on Wall Street. You can think of it as a very like a shallow kind of like normalizing flow, where you only apply one layer of Gaussianization on each individual dimension. So you start with data that is not Gaussian distributed, then you apply this Gaussian CDF trick to basically make each individual dimension Gaussian. And even though jointly it's not Gaussian, that's your model of the data, and then you can stack them together, and then you get, if you keep doing this thing and you apply some rotations, then you can transform anything into a Gaussian, and this is another way of basically building invertible transformations. But I'm out of time, and so I think this is a good point to stop.